Hey everyone, Mr. Johnston here. In this video, we're going to be reviewing a little bit of some of the symbols we're going to be using in this unit, the three main equations that are going to be kind of a big deal coming up over and over and over, and then really heavily kind of doing a couple practice problems with the algebra with some of these problems. Now, before that, we're going to need some colors today, so if you'd actually take a minute and hopefully get out 4 different colors. I am actually looking and expecting that you use some different colors here, so please get those out. I'm going to use red, blue, green, purple, and then kind of just like black pen or pencil. So once you've done that, let's just put down what the 3 main equations for this unit in fact are. So we have, the 3 equations in this unit are, and then we'll go blue for the first one, and I'm skipping one line. V equals delta x over delta t. We're calling that delta as this Greek letter. The second one I'm going to use red for is A, not that red, this red. A equals delta V over delta t. And then the third equation is kind of the long one, kind of the tricky one a little bit, or at least it looks more intimidating. It ends up being just about as easy, if not easier. But we have x, and I'm using green now, my third color. Final, little subscript says final kind of down below, equals x initial, little subscript down below, plus 1/2 a t squared. But wait, there's more, plus v initial times t. So wow, we got these 3 equations for the unit. Sweet. Now let's go over like what the heck some of these symbols are. So I'm going to go back to my black. I have one color that I'm still holding out on using. We'll go symbol. And then over here we'll write the meaning. And we're going to go down, starting at the line above symbol 1, 2, 3, 4, 5, 6, 7, 8, 9. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. Go across. And the symbols we have are V, delta, X, T, A. Now we have X final, X initial, and V initial. Now I'm actually just going to give a moment here for you to actually just think about what each of these are. Maybe pause the video, or if I'm not here, have the video paused. And I want you actually to go and fill in with your partner, hopefully with pencil, what you think each of these symbols actually means. So just take a moment and do that. And sweet, let's fill it in. So V is speed. Speed usually, and I'll put in parentheses the units, speed is usually in like meters per second or centimeters per second. We don't deal with the whole miles per hour thing because we're in science class and it's English units. Triangle is delta. The letter delta means, in quotes, change in. All right, sweet. X is distance, essentially how far it's gone. This will usually use meters or centimeters. T, time, pretty much always use seconds here. A is acceleration. That's usually in meters per second squared. Sometimes you'll see in a textbook, or typically I actually like to say meters per second per second because it's how much you're speeding up. So you have speed changing, so meters per second divided by seconds. So that's kind of the way that I like to write it typically. But oftentimes we'll see it as meters over seconds squared just because it looks a little more compact. X final is the final distance, obviously. Hopefully that makes sense. Final distance, how far it's gone by the end. You can even write at end. X initial is the initial distance. What a surprise. That would be at the start. And V initial, well, V is speed. This must be the initial speed. That means at the start as well. Now, I'm actually going to grab my fourth color for a little note here. And I have kind of some space over here on the rightish side of all this stuff I just put in black where we have meaning. And my note is going to be the following. We usually just call X initial 0 because objects usually start at 0. And this is all going to go for right there. So X initial, it's in this equation up here, the third one in green. Pretty much all the time, you're just going to call X initial 0, and then you just have one less thing to worry about. That's kind of all there is to it. So now let's actually just do a couple examples. So you're going to need some kind of calculator for this. If you're at home doing this, totally just whip out the phone calculator. If you're in class, go have one person from your table get calculators that match your table color, and everyone take out a calculator. And hopefully you can enter in, I don't know, the number 20 or something, and actually spits out 20, not like a 2.0 or something like that. If it says 2.0, blah, 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 take your pencil, flip the calculator upside down. There's a little reset button on the back. Just poke the reset button. You should be good to go. But now let's actually do some examples. So I'm going to go skip one line. Examples / practice. And so number 1, we're going to write down the question because later you're going to partner teaches probably someone on another day. And so we have you are in the car and travel 20 meters. So you travel 20 meters every 4 seconds in the car. Period. How fast are you moving? Now, I will mention for this part, I'm going to kind of switch back and forth between colors a little bit just because I want it to pop a little bit and it can make more sense to you, hopefully. I'm a very visual person. If you really just want to use a whole lot of pencil here or pen, that's totally fine if it just seems like I'm going a little too quick. And so let's look at what we have here. You can underline the stuff that I highlight. We have 20 meters and 4 seconds. So I'm essentially looking for like, what are the numbers that were given here? So 20 meters, that's a delta X. That's just how far something's gone. This 4 seconds, that's got to be a delta T. That's how much time has passed. This how fast thing. Well, fast means speed. Speed is V. So it gave us delta X. It gave us delta T. It's asking for V. Sweet. So on the next line down, I'm just going to put our givens. Givens. We are given that delta X is 20 little m. It's the unit for meters. Delta T is 4 seconds. The little s is for seconds. And now here I actually have to mention what the hardest part of this unit is probably going to be. It's going to be figuring out which equation is the appropriate equation to actually use, because we have three. We have three of them, and it's asking us for how fast we're moving. And so it's asking for speed. Well, I see a V in all three of these, so I don't know which one I actually want to use, essentially. So maybe we can get lucky with just trying the first one, though. So this first one here, sorry, I thought I was just going to sneeze there, actually. This first one, it has speed, V, and we're trying to find speed, so that checks out. And it needs us to know the distance, and it needs us to know the time. And when we divide the distance by time, well, we know it's gone 20 meters. We know it takes 4 seconds. This first equation will totally work. So let's use that one. So V equals delta x over delta t. And then I'm going to go one space to the right a little bit, right, solve. And I'm doing it in this special way because this is how you're going to be doing this actually on a worksheet. That's just going to be some practice of using these. And so it's kind of the guess method. It's not really guessing. It's G's for givens, E's for equation, S's for solve. So we'll kind of go through these 3 steps, and it'll make it really easy, hopefully, or easier at least, to go ahead and actually solve these maybe seemingly very challenging problems. So to solve this, V is, we just have to plug in 20 meters over 4 seconds. Well, that just equals 5 meters over seconds. And that's it. That's how fast you'd be going in the car. Cool, easy. So essentially figure out what the heck they give you, write out the givens, write out the equation, figure out which is the correct equation based on the givens, and then just plug in. Let's look at a second example here. So let's say that we have a bowling ball and it's at rest. A bowling ball at rest accelerates, so it speeds up, accelerates at 6 meters per second squared for 3 seconds. How fast will it be going? Okay, so again, let's figure out what the heck we're given here. Accelerates. Okay, so we know A. Sweet. 3 seconds. Cool. We know time. And how fast? Well, wait, isn't that V again? So it's asking for V. It just gave us different stuff this time. That's kind of all that's really different here. So let's go through. Let's do our G, our givens. Then we'll do the equate. We'll figure out what the correct equation is. We'll solve. It'll be quick. It'll be easy. We'll be on to our third one, and then we'll kind of be all done with this page. So givens. We're given that A is 6 meters per second squared. We're also given that delta t is 3 seconds. All right, let's figure out the equation then. We know A, we know T, we need V. We know A, we know T, we need V. Well, this one has V. That's what we want. And we know T. That's pretty handy, but we don't have X. We don't know how far it's gone. We can't use the first one. That one just straight up doesn't work. Second one, we're given A. It speeds up at 6 meters per second squared. We're given T, goes for 3 seconds, and we're asking to find V. We could totally use the second one here. We can solve for V. We can plug in A. We can plug in for T, and we'll actually get V right there, no problem. So let's use the second one. Should have been color coding this actually. So we have A is delta V over delta T. But this was kind of the awkward part. This one isn't already solved for V alone. So we have to do algebra essentially. And now you can choose to just plug in the numbers right now or plug them in later. I'm actually going to do both just to kind of show, and you can kind of pick and choose which one makes more sense to you. So maybe just sit back for a second and see which one is maybe easier for you. I'll kind of do just the plug-in method first. So the plug-in method, you'd have 6 meters per second squared equals delta V over 3 seconds. Well, if I'm trying to get V alone, I would actually have to go ahead and multiply by 3 seconds on this side. And if I do it on the right side, I have to do it on the left side as well. And so I can see actually here that I'll use purple. These 3 seconds cancel on the right side. We just have delta V alone. And so really we have to do 3 times 6. So 3 times 6 is 18 meters per second is delta V. So that's kind of the first way that you can totally go ahead and solve this. And I want to mention here, how the heck did the units work out? It turns out that like since you're multiplying by seconds here, but then you're dividing by seconds twice there, the seconds that you're multiplying by gets canceled out, just like that. And then that cancels with the squared up here, and then you just have meters over seconds. Now, the second way that you could have solved this is just by plugging in later, essentially. So you could have kind of taken this equation, and you don't have to write this part unless you really want to. You could totally say multiply by delta t here, and then multiply by delta t here, and then you end up having delta t times a is our change in speed. And then you could have just plugged in right here at the very end. Both work. They're both equally correct. You'd end up still doing 3 times 6, and you'd still get the same 18 meters per second. Just pick whichever one makes more sense to you. Do algebra in the beginning to get the thing you want alone, or plug in and then just do algebra to get the thing you want alone. You're doing the same thing essentially. So just kind of pick whichever one it is. And now for our third and final example here. So there's a Tesla Model S Plaid. This car is stupidly fast. It has 0 to 60 in 1.99 seconds, which is scary fast. Like you go faster, you speed up faster in the car than you would if you jumped off a building, which is kind of saying a lot. So a Tesla Model S Plaid. It's just the really bougie, fancy, expensive, sporty version. Tesla Model S Plaid is stopped at a red light. Okay. It turns green. And the car accelerates at 13 meters per second squared for 3 seconds. How far does it go? So let's break this down. It stopped. Okay, so we know the initial velocity stopped. V initial is 0. That's pretty sweet. Turns green. Car accelerates at 13. Okay, so we know A. Awesome. For 3 seconds. Okay. I said 3 second. Sneak a little S in there. Cool. So we know the delta T. And what the heck is it asking for? How far? How far is like a distance? So that's actually asking us for delta X or like X essentially. Like how far has it gone? So this is kind of a tricky one actually. Let's set up our givens. So we've been given that V initial is 0. We've been given that A is 13 meters per second squared. We've been given delta T is 3 seconds. Now, really, I want to mention here that delta T is kind of just the same thing as T. Like how much time has passed? Well, that's what the time is. Typically, you assume that like you're starting at 0. So if you start at 0 and you wait 3 seconds, 3 seconds have passed, and the time is going to be at 3. So we could also just kind of call this T as well. It really doesn't change it in this case here. And then there's a little note I said earlier. We get to call just X initial 0 because things start at 0. And so we're just going to say that x initial here is 0 meters. Just get to call where it starts 0. That's pretty sweet. So now let's figure out the equation. Now we're trying to find x. So looking at these just right off the bat, this first one has x. The second one doesn't even have x. The third one has x. So the second one's kind of off limits. So it's either the first or the third. So the first one looks a lot easier to me. So if we know the speed and we know the time, we can find how far it went. So let's look back. We know the time. So that works. And do we know the speed? That the speed's actually always changing. You're stepping on the gas in the car, so it's going faster and faster. So we actually don't know the speed and we don't know the distance. We cannot use number 1, the first equation in blue. If we can't use the second one, well, hopefully the third one's going to work for us. So we're going to have to figure this one out. Now, the nice thing though, and you don't need to write all over yours, is that since we're dealing with kind of some assumptions here, we get to call the initial position, or like where it's at, 0 in the beginning. And initially, since it was stopped at a red light, V initial is also 0. So if this thing is 0 and this thing is 0, this got a lot easier actually looking. So let's actually go and set this up down here. X final equals X initial plus 1/2 AT squared plus V initial times T. But we said since it was stopped at a red light, this V initial is 0, and that times time is still 0. So this thing, put a little arrow through it, say that's 0. We get to call where it starts 0, so this X initial is also 0. So I'm just going to rewrite it kind of cleaned up. X final equals 1/2 AT squared. Now, does that work? We want to find where it is, how far it has gone. So that works. We're trying to find X final, and we need to know the acceleration and the time. We know the acceleration, we know the time. That's it. Money right there. Let's plug in and solve this thing. Solve. X final equals 1/2 13 meters per second squared times the time squared. So 3 seconds squared. And so you're actually gonna have to bust out a calculator for this one, because this is kind of some hard mental math. You know that 3 squared is 9, and then 9 times 13 though, I'm not sure on that one. I actually don't have my calculator with me, hilariously enough. I think 9 times 13, 117, and then that cut in half, we get 58.5. 58.5, and since it's a distance, it should be in meters. Done.